Hello everyone, this is Nikilian, Assistant Professor, Department of Civil Engineering, AJT Mangalore. So in our previous session, I had discussed about some numericals in losses of prestress. So in today's session, let us continue with the discussion of few more numericals. So firstly, let us consider a simple problem. So here, a simply supported post-tensioned concrete beam having a span of 15 meters is a rectangular cross-section of 300 by 500 mm. The pre-stressing force at ends is 1300 kN with zero eccentricity at supports and having an eccentricity of 250 mm at midspan. The cable profile is parabolic, assuming K is equal to 0.15 per 100 meter and mu is equal to 0.35. Determine the loss of prestress due to friction at the center of a beam. So here in this question they have asked us to calculate what is the loss of prestress due to friction in the given beam. So for this beam, a initial prestressing force is applied from both the ends. So here they have mentioned the prestressing force at both the ends is 1300 kN. So let us consider a beam of cross section 300 by 500 mm whose length is 15 meter. So the cable profile given is a parabolic cable profile where the eccentricity is 250 mm at midspan and 0 at ends. So a pre-stressing force of 1300 kN is applied at this end and this end. So we know the formula to calculate loss of pre-stress due to friction. So the formula to calculate the loss of pre-stress due to friction is equal to Fsi into Kx plus mu theta. So Fsi is nothing but it is initial pre-stress. But in the question, they have not given what is initial pre-stress. They have given what is initial pre-stressing force. That is the initial pre-stressing force is 1300 kilonewton. And K is given, it is 0.15 per 100 meter. X we can calculate from a given condition. Mu is given and theta we should calculate from the given condition. So here the cable is being pulled from both the ends. When the cable is pulled from both the ends, slope is equal to 4R by L. So 4 into R by L is the slope, where R is the central dip or R is the eccentricity at midspan. So 4 into 250 by L. L is length of a beam, that is 15 meters. In terms of millimeters, it is 15,000 millimeter. Therefore, slope is equal to 0.0667 radian. And x is equal to L by 2. X is equal to L by 2 because the cable is pulled from both the ends. If the cable was pulled from only one end, then x is equal to L. So here the cable is being pulled from both the ends. Therefore, x is equal to L by 2, which is equal to 15,000 by 2, and x is equal to 7,500 millimeter. And theta is equal to 1 into slope. Theta is equal to 1 into slope because the cable is pulled from both the ends. So substitute the values in this formula. So Fsi, initial pre-stress, is not given. So we know that pre-stress or stress is equal to force by area. So force is given and we can calculate what is area, or else we can keep A as it is without substituting any value. So here I am going to substitute Fsi is equal to, that is initial pre-stress. Initial pre-stress is equal to initial pre-stressing force by area. So here I will substitute force by area. So force is initial pre-stressing force is 1300 kilonewton. So here 1300 kilonewton divided by A. So there is a mistake there. So it should be 1300 into 10 to the power of 3 Newton by A. So force by area, that is equal to initial pre-stress. The value of K is 0.15 per 100 meter. So 0.15 divided by 100 into 10 to the power of 3. So 100 meter has been converted into millimeter, into the value of X is 7500 plus mu is equal to 0.35 into 0.0667 is the slope, and which is equal to theta. Therefore loss due to friction is equal to 44.9 into 10 to the power of 3 divided by A. The loss due to friction is equal to 44.9 into 10 to the power of 3 divided by A. So A is this one. So force 1300 into 10 to the power of 3 divided by A. So that A, let us keep like that. So here it will become 44.9 into 10 to the power of 3 divided by A. Therefore percentage of loss of pre-stress is equal to total losses divided by initial stress. Total loss of pre-stress divided by initial pre-stress. So we can write total loss of pre-stress is equal to FSI divided by A. So we know that total loss of pre-stress due to friction is equal to 44.9 into 10 to the power of 3 divided by A, and initial pre-stress. So initial pre-stress is not given. Let us consider initial pre-stressing force. So pre-stressing force is 13,000 into 10 to the power of 3 divided by A. That gives us initial pre-stress. So here A and A will get cancelled, and remaining term will be 44.9 into 10 to the power of 3 divided by 1300 into 10 to the power of 3 into 100. That gives us 3.46. So percentage of loss is equal to this much. So this is the percentage of loss of pre-stress due to friction. Let us go to the next example. So here the question is, a post tensioned cable of a beam 10-meter long is initially tensioned to stress of 1000 Newton per mm square at one end. If the tendon is curved so that the slope is 1 in 24 at each end with cross-sectional area of 600 millimeters, calculate loss of pre-stress due to friction with the following data. So the data is given are coefficient of friction between duct and the cable is 0.3, that is mu is equal to 0.3, and friction coefficient for wave effect is equal to 0.0015 per meter, that is K is equal to 0.0015 per meter. So here in this problem they have asked us to calculate what's the loss of pre-stress due to frictional effect. So here a stress of 1000 Newton per mm square is applied, and the stress is applied only from one end of a cable, and the tendon or a cable is having a curved profile, and it is also given that the slope of a cable is 1 in 24. So this is the slope given, theta is equal to 1 by 24. Therefore tan theta is equal to 1 by 24 is the slope. Therefore theta is equal to tan inverse of 1 by 24. Hence theta is equal to 0.0417 radian. So this is the theta. And remember that the cable is pulled from only one end. Therefore theta is equal to slope into 2. 0.0417 into 2. Hence theta is equal to 0.0834 radian, and x is equal to 10 into 10 to the power of 3 millimeter. X is equal to L, and we know the formula to calculate loss due to friction, that is FSI into mu theta plus K into x. So loss is equal to FSI is initial pre-stress, it is given, it is 1000 Newton per millimeter square. 0.3 mu is given, theta we have calculated by the given slope, plus K is given into x. So loss is equal to 40 Newton per mm square. Therefore, percentage of loss of pre-stress due to friction is equal to total loss due to friction divided by initial pre-stress. So total loss due to friction is 40, and the initial pre-stress that was applied to the cable is 1000 Newton per mm square. So 40 divided by 1000 Newton per mm square into 100, that is equal to 4%. So loss due to friction in the cable is 4%. So this is what they have asked in the question. And now let us take up one more example. So this question was once asked in the semester exam. There is a post tension beam of span 10 meter, and here for this beam we need to calculate what is the jacking force at left end. That is, we need to calculate what is the initial pre-stressing force that was applied at the left end, and also we should calculate the total losses of stress in the wires. So the details what they have given is, they have given the span of a beam. The span of beam is 10 meter, and the cable is having an eccentricity of 250 millimeter at the mid span. The cable is having a parabolic profile, and they have also given that the force, initial pre-stressing force in the cable at right end is 250 kilonewton. So remember this, initial pre-stressing force at right end, that is 250 kilonewton, and we need to calculate the initial pre-stressing force at left end. And also they have given the details for shrinkage of concrete, creep of concrete, and they have given what is the amount of anchorage slip. They have given the coefficient of frictional values, etc. So for this we should calculate force at jacking end and losses in the wires. And here in the question we should note that the cross section of a beam is not given. So he has given only the span of a beam. The span of a beam is 10 meter, and he has not given what is the width of a beam and what is the depth of a beam. So when this kind of question is given in the examination, first we should assign the cross sectional details for a beam. So let us assume the overall depth of the cross section as 50 mm per span. Let the section be provided as rectangular section. Therefore, overall depth D is equal to 50 into 10. 10 is span of a beam. Therefore, overall depth is equal to 500 millimeter. Since eccentricity is given and the eccentricity is 250 mm at the mid span, and we should provide a cover of at least 50 mm to 100 mm. Therefore, let us provide a depth of cross section as 600 mm by considering the thickness of covers from 50 mm to 100 mm, and by considering the eccentricity, let us make the depth as 600 mm. And let us consider width of the cross section, or width of the beam is equal to 0.5 into 600, that is 300 mm. So this is the cross section of a beam. Depth is 600 mm, width is 300 mm. So here we can see the depth of a beam and length of a beam. So the length of a beam is 10 meter and depth of a beam is 600 meter, and it is a rectangular section. The central axis lies at the distance of 150 mm from both the ends. So here the cable profile is parabolic and the cable is having an eccentricity of 250 millimeter at midspan. So this is the eccentricity of a cable at midspan. So let us consider this as left end and this as right end. So what is given? So the force is applied only from one end. So let us consider the force is applied at the left end. Let us consider this as the left end. So the force is applied. Initial pre-stressing force is applied from this end, and this end is anchored because the force is applied only from the one end. So from this end the force is applied and this end is anchored. We don't know what is the initial pre-stressing force applied at this left end, but we know that the initial pre-stressing force at this end is 250 kilonewton, and we know that the initial pre-stressing force at jacking end will be more than this end. That is, the initial pre-stressing force at left end will be more than right end because here the force is applied and there is no loss of force due to friction. When the force travels from this from this end to this end, there is a loss of force. There is a loss of pre-stressing force due to friction developed between the surface of ducts and the cables. So here the friction will be developed between the cable and the duct, and due to this friction there is a loss of initial pre-stressing force. Hence we can tell that the initial pre-stressing force at left end will be more than that of right end. So here the initial pre-stressing force at right end is 250 kilonewton. Therefore, the initial pre-stressing force at left end should be more than 250 kilonewton. Here the force at jacking end will be more than force at other end. So in the question, they have given the cross-section area of a tension steel. So the cross-section area of tension steel ATS, that is 500 millimeter. So we know cross-section area of a tension steel, and we know what is the initial pre-stressing force at right end. Therefore, I can calculate what is the initial pre-stress at right end. We know stress is equal to force by area. So we know what is the cross-section area of a cable. We know what is the initial pre-stressing force at right end. So with the help of this force and area, we can calculate what is the initial pre-stress. So initial pre-stress available at right end. Initial pre-stress available at the right end, FSI is equal to F naught by ATS. F naught is initial pre-stressing force at right end. ATS is the cross-section area of a tension steel. Therefore, FSI is equal to 500 Newton per mm square. Initial stress at right end is equal to 500 Newton per mm square. So here, first we should calculate what is the initial pre-stressing force, or what is the initial pre-stress applied at this jacking end. So we know the initial pre-stress at this end is 500 Newton per mm square. So 500 Newton per mm square is the stress at this end after the loss due to friction. So if friction loss is added to this 500, then I will get what is the initial stress at left end. So first what I should do, I should calculate what is the loss of stress due to friction. So I know what is the formula to calculate the friction loss. So the formula is Fsi into mu theta plus Kx. So the unknown things are theta, Fsi is unknown, that is initial pre-stress at left end is unknown. Let us keep it as it is, and the value of K is given, the value of mu is given, and the value of X can be calculated by the given condition. So here the cable is pulled from one end, therefore theta is equal to 2 into slope. Theta is equal to 2 into slope, whereas slope is equal to 4r by L. So slope is equal to 4r by L, where r is the central dip, that is 250 millimeter. So theta is equal to slope into 2. So by simplifying this, theta is equal to 8, that is 4 into 2, it is 8 into r is 250 millimeter, 0.25 in terms of meter divided by 10. That gives us 0.2 radian. So theta is equal to 0.2 radian, and L is equal to X. So L is the span of beam, therefore L is equal to X, or X is equal to L, which is equal to 10 meters. Therefore, loss of pre-stress due to friction, this is the formula. So substitute the calculated values in this formula. Mu is given, theta we have calculated, it is 0.2 plus K is given, X is equal to L, because the cable is pulled only from one end, therefore X is equal to L, it is 10 meter. Fsi, that is initial pre-stress at left end, which is not given, so let us keep it as Fsi only. Therefore losses due to friction is equal to 0.14 Fsi. So this is the friction loss occurring when the force is traveled from this end to this end. When the force has moved from this end to this end, the loss is 0.14 Fsi is the loss. And we know that the stress or force, the pre-stressing force or pre-stress which is applied at left end will be full. If I am going to apply a pre-stress of 1000 Newton per mm square, then the stress at this point will be 1000 Newton per mm square only. The losses at this end will be 0. The losses of pre-stress at jacking end is 0 due to friction, because there is no friction at this jacking end. So we can tell that pre-stress at left end will be 100%. That is equal to 100% of Fsi is present. So here the pre-stress is full. We have 100% pre-stress here at left end or jacking end, and the pre-stress has been reduced by 0.14 Fsi due to the friction between the cable and the duct, and here the pre-stress is 500 Newton per mm square. So we know that pre-stress at left end will be 100%, which is equal to 100% of Fsi is present. So next, the stress available at the other end. So what will be the stress at this end? So the stress at this end will be equal to 100% stress. 100% stress which is applied at this end minus losses, we will get stress at this end. So that is what shown here. Stresses available at other end is equal to 100% FSI minus losses. So we already know what is the stress at other end. We already know what is the stress at this end. So the stress at this end is 500 Newton per mm square. So that is 500 is equal to 100% FSI minus loss. 100% means it is 1 into FSI minus loss is 0.14 FSI. So 1 FSI minus 0.14 FSI is equal to 0.86 FSI. Therefore, stresses at left end is equal to 500 by 0.86. So from this equation, stresses at left end is equal to 500 by 0.86, that is equal to 581.4 Newton per mm square. So the stress at right end was 500 Newton per mm square, and the stress at left end is more than that, 500 Newton per mm square. It is 581.4 Newton per mm square. So the total loss of stress from 0 end to 10 meter is 81.4 Newton per mm square. Therefore, the force applied at jacking end, we know what's the stress at left end, and we know cross section area of a tension steel. Therefore, initial pre-stressing force is equal to stress into area. So stress is 581.4 into area is 500. So 290.6 kilonewton is the initial pre-stressing force which is applied at left end. So we have calculated the first case, that is the initial pre-stressing force at left end. So we have calculated the first case. Now coming to the second case. The second case is to calculate the total losses of pre-stress in the cable. So first let us consider loss due to anchorage slip. So we know the formula. The formula to calculate loss of pre-stress due to anchorage slip is equal to delta A into ES by L. So they have given what is the amount of slip in the anchor, that is 3 mm, L is 10 meters, in millimeters it is 10,000 into 2.1 into 10 to the power of 5, which is Young's modulus of steel. Therefore, loss due to anchorage slippage is equal to 31.5 Newton per mm square. Now let us calculate let us calculate loss due to elastic shortening. So to calculate the loss due to elastic shortening, to calculate the loss due to creep, we need FC. That is, we need the compressive stresses developed in the concrete with respect to the CG of tendons or CG of a cable. But here we have two different eccentricities. We have eccentricity of 250 mm at the midspan, and we have eccentricity of 0 at the ends. So for this both the conditions, different stresses are developed in the concrete. Different compressive stresses are developed in the concrete. So we should calculate the compressive stresses for both the cases. We should calculate what's the compressive stresses developed due to 250 mm eccentricity, and also what is the compressive stresses developed in the concrete due to eccentricity of 0 millimeter. So first let us consider the eccentricity at midspan, and let us calculate the compressive stresses. So compressive stress developed at the level of CGs of tension steel at midspan, FC1. So we know this formula to calculate FC, that is F naught by A plus F naught E1 square by I. So F naught is initial pre-stressing force, I is moment of inertia. Moment of inertia is equal to BD cube by 12. So BD cube by 12, moment of inertia is equal to 5.4 into 10 to the power of 9 mm to the power of 4. Area is 600 by 300, which is 1.8 into 10 to the power of 5 mm square. Therefore, Fc1 is equal to, substituting all these values in this formula, Fc1 is equal to 4.966 Newton per mm square. So this is the compressive stresses developed in the concrete due to an eccentricity of 250 millimeter at midspan. Then what's the compressive stresses developed in the concrete due to eccentricity of 0 mm at the ends? So let us calculate compressive stresses developed at the levels of CGs of tension steel at support, that is FC2. So previous one we were taken as FC1, and this one let us take as FC2. So FC2 is equal to F0 by A plus F0 is E2 square by I. So here the eccentricity is 0 because we are considering with respect to the support, and at the support the eccentricity of cable is 0, so this term vanishes. Therefore Fc2 is equal to 2.5 into 10 to the power of 5 divided by 1.8 into 10 to the power of 5. Therefore Fc2 is equal to 1.389 Newton per mm square. So why we need to calculate compressive stresses for different eccentricities is because with respect to the different eccentricity the losses will vary. Hence we will calculate the stresses at different eccentricities. Now we have two compressive stresses with respect to two eccentricities. Then what will be the resultant compressive stress with respect to the CG of a tension steel? So the resultant stresses will be like this. If we draw a stress diagram, so this is Fc2, this rectangular portion is Fc2, this is the stress diagram due to end eccentricity of 0 mm, and this is this parabolic portion is the compressive stresses developed due to eccentricity of 250 mm. So this is the stress diagram for both the cases. Therefore, the resultant compressive stresses, resultant Fc is equal to, so remember this equation, resultant Fc is equal to Fc2, that is Fc2 adding all this portion is the resultant stress. So Fc2 we know it is 1.389. So this portion plus this parabolic portion. So Fc2 plus what is the remaining portion here? This portion it is 2 by 3. 2 by 3 because it is a parabolic portion. So 2 by 3 into Fc1 minus Fc2. So Fc1 means it is from year to year. Fc1 is from, you can see here from year to year it is Fc1, and already we have taken this depth as Fc2. Therefore the remaining portion, this remaining portion is Fc1 minus this depth. So Fc is equal to Fc2 plus 2 by 3 into Fc1 minus Fc2. So you should remember this condition. Therefore Fc is equal to 3.77 Newton per mm square. So the resultant compressive stresses in the concrete with respect to CGs of tensioned steel is equal to 3.77 Newton per mm square. Now let us calculate different losses. So firstly, loss of prestress due to elastic shortening is equal to 0. It is 0 when the cables are pulled simultaneously. If there are 10 cables and all the 10 cables are pulled together, then the loss due to elastic shortening is 0 in case of post-tensioned member. So second loss of prestress due to creep of concrete, CCMFC. So here creep coefficient is given. They have not given ultimate creep strain. Creep coefficient is given, hence we are using this formula. So creep coefficient is 2.2, m it is Yes, Young's modulus of steel by Young's modulus of concrete, which is given in the question, into FC, resultant compressive stress, we have calculated here. So substituting the values, we will get loss of pre-stress due to creep of concrete is equal to 49.76 Newton per mm square. Loss due to shrinkage of concrete. So we know the formula delta S into ES. So delta S, shrinkage coefficient is given in the question. ES, it is Young's modulus of steel. The value is given in the question. Therefore, loss due to shrinkage is equal to 42 Newton per mm square. Then loss of pre-stress due to relaxation of steel. So they have only given in the question the loss due to relaxation of steel is 4% of initial pre-stress. 4% of initial pre-stress. So 4% of FSI. So initial pre-stress 4 by 100 into 500 initial pre-stress. Therefore, loss due to relaxation of steel is 20 Newton per mm square. Therefore, total loss of pre-stress in the wire or in the cable is equal to 0. 0 is due to elastic shortening. 49.766 plus 42 plus 20, that is equal to 111.76 Newton per mm square. So this is the second case, total losses in the cable.